Hello and welcome to the NSF Future Manufacturing Data Challenge. This challenge focuses on predicting how the geometry of a laser track changes from one physical location to another during directed energy deposition, or commonly known as DED process. The central idea is to combine the in situ thermal history of the laser material interaction with the local morphology of the substrate. Instead of predicting one average value for an entire track, participants are asked to predict local geometry and its uncertainty along the scan path. The three principles to keep in mind are: predict locally, quantify uncertainty, and preserve physical alignment. To understand why this local formulation is necessary, let us first look at the manufacturing problem. Even with the process settings are held constant, a laser track is not perfectly uniform. Its width, left and right boundaries, surface contour, and edge waviness can vary continuously along the scan direction. A single global width value hides these variations and therefore gives us an incomplete description of the final track. Some of these variations are process-driven. The thermal history reflects melt pool size, shape, intensity, and cooling behavior. Other variation is substrate-driven. Valleys, ridges, local surface irregularities can influence how the molten region spreads and resolidifies. The challenge is therefore to predict the local geometry denoted by G sub I of x at each position x. With that problem in mind, the next slide summarizes how the dataset was generated. The dataset consists of a single bead-on-plate laser scans performed on a stainless steel 316L substrates using Optomec MTS hybrid DD platform. 4 laser powers were investigated: 200, 300, 350, and 400 watts, while the scan speed was fixed at 10 millimeters per second. The realized experiments correspond to track IDs 8, 10, 14, and 21. For every track, the analysis focuses on a shared physical interval from approximately 20 to 100 millimeters. With this common interval, three complementary measurement modalities describe the same physical track. The first modality is the in situ thermal image sequence. Each thermal frame contains 400 by 400 pixels, is recorded at 50 frames per second, and has a spatial resolution of approximately 14 micrometers per pixel. These frames capture the moving melt pool and its thermal neighborhood, including size, shape, temperature distribution, and the cooling tail. The second modality is SEM imagery. The SEM image describes the local substrate morphology, including valleys, ridges, and texture around the scan path. The processed track itself must be masked or excluded when SEM features are used, because otherwise the model could directly observe the final geometry and create a data leakage. The third modality is the Bruker or Vico height map. It provides the post-process surface geometry and is used to extract the ground truth targets, such as local width, boundary position, waviness, or contour descriptors. Because these measurements come from different sensors and file formats, the key challenge is to align them in a physical space. Before defining the final input-output pair, it is important to understand how one physical location is represented across the three modalities. Let us consider a specific coordinate xj along the scan direction. Because the melt pool is moving continuously, that location does not appear in only one thermal frame. Instead, it is visible in several neighboring frames as the melt pool approaches, passes over, or moves away from the xj. We therefore represent the thermal input as a short video tensor, referred as Tij, containing 2k plus 1 frames, centered around the time associated with that location. At a fixed scan speed of 10 millimeters per second and a frame rate of 50 frames per second, adjacent active thermal frames correspond to approximately 0.2 millimeters of laser travel. This creates overlap between neighboring frames and allows the tensor to capture heating, multiple behavior, and cooling around the same physical location. The next challenge is to coordinate alignment. The modalities are not stored in the same direction or indexing convention. For the SEM data, image 01 corresponds to the 100 mm side of the track, while the highest numbered image corresponds to the 20 mm side of the track. Therefore, for a selected coordinate xj, we first identify which SCM image covers that position, extract the local morphology patch, and mask the processed track region to prevent the target leakage. The height map data also requires correction. In the raw ASCII file, local x equals to 0 corresponds to the physical 100 mm side. The columns must therefore be reversed or sorted into increasing physical coordinate order before common 20 to 100 mm region is extracted. Once these corrections are applied, all modalities refer to the same physical coordinate. We can then combine the thermal tensor, masked SCM morphology, and the metadata to predict the local geometry GI for xj position, such as the width together with its uncertainty. Now the thermal sequence, SCM image, and height map target are aligned to the same location. We can formally define one complete model input-output pair. This is one of the example on how SCM tiles are presented in the dataset that you have. For example, on the rightmost image, we have an image named plane SCM 8_13. 8 is the track ID and 13 is the image number. It represents the first image, basically corresponds to 20 mm. And if you place the next image on the left side of the first image, you get closer to the 100 mm. And the last image, 801, corresponds to the 100 mm image. Consider one physical location, X, along the track. The first input is a short thermal tensor around that location. As mentioned before, this sequence provides the local thermal history of that particular point. The second input comes from the SCM image. Remember to exclude the scan track and it must remain masked. Additionally, you can use metadata, which include the physical coordinate, laser power, as well as the track identity. Or you can derive a couple of other parameters such as energy density. The model then predicts a probability distribution for the local geometry. In the equation shown here, G sub I is the geometry at position X for track I. But the important point is that output can be probabilistic. Therefore, the model should communicate both its expected prediction and its uncertainty. Local width is the main target, but the dataset supports several richer definitions of the track geometry. The expected target is the local track width at each coordinate x, extracted from the process height map. However, participants may also define richer targets, such as the left and right boundary position, contour deviation, edge roughness, waviness, or a vector containing local descriptors. For example, a model can produce a mean width curve together with an uncertainty band across 20 to 100 mm interval. A strong submission is not only accurate, it is also calibrated. In other words, when the model reports high or low uncertainty, that uncertainty should be consistent with the actual prediction errors. The next slide translates this task into a practical processing and modeling workflow. A recommended workflow contains 6 main stages. First, load the thermal mat files, SEM TIFF images, and ASCII height maps. Second, convert all units consistently, including pixel positions to millimeters and height values from nanometers to micrometers or millimeters. Third, correct the coordinate direction and crop the shear 20 to 100 mm interval. Fourth, Construct aligned training pairs by associating each thermal sequence and masked SEM morphology with the geometry target at the x-coordinate. Fifth, train either a single modality or a multi-model probabilistic model. Finally, evaluate the model on a held-out track using both prediction accuracy and uncertainty quality. Throughout this workflow, preventing SEM target leakage is essential. The choice of validation strategy is especially important because the dataset contains only 4 track conditions. Randomly splitting neighboring coordinates from the same track into training and testing sets can produce overly optimistic results. Adjacent locations are spatially correlated, so the model may effectively see almost the same region. For this reason, cross-track validation is recommended. One complete track should be excluded during training and used only for testing. Track 21 is useful conservative held-out case because its profilometry coverage is less complete, which tests the robustness to imperfect post-process measurement. Possible evaluation metrics include mean absolute error for local width, boundary position error, log likelihood, or a continuous ranked probability score for the probabilistic predictions, calibration error, and uncertainty interval coverage. These elements lead to the final message for the challenge. In summary, the challenge asks participants to combine a local thermal sequence, a masked SEM context, and the physical coordinate of interest to predict a probabilistic local geometry distribution. There are 3 main takeaways. First, predict geometry locally along 20 to 100 millimeter analysis window rather than reducing the track to one global number. Second, preserve alignment across thermal SEM and height map measurement. Third, report uncertainty together with the prediction. We look forward to seeing the innovative approaches you develop using this dataset. Thank you for participating in the NSF Future Manufacturing Data Challenge, and we wish you all the best in the competition.